Okay, just a quick recording here. Someone asked for questions 7, 8 and 9 from the 2015 test 2. So a few people have asked about this question here, so I'll do it and I'll do the next two as well. So 3 parallel infinite conducting sheets have uniform positive surface charge density of sigma, 2 sigma and 3 sigma. What is their order from left to right if the electric field produced by the arrangement has magnitude E equals 0 in one region, E equals 4 sigma on epsilon naught in another region? Okay, and here's some potential orderings. Well, let's do one of them and see what happens. So I'll do the first one. So sigma, 2 sigma, 3 sigma. Okay. And this is the, if you look in the formula sheet, it's going to tell you that near a uniformly charged sheet, conducting sheet with surface charge density sigma, the electric field is equal to sigma over epsilon naught. So therefore, if we look at this sheet here, it produces a field in either direction like so. Now they're infinite sheets, and that means that this field extends onwards. It's also present here, it's also present here, it's also present further along here. Okay, so if we want to find the electric field at any one point, we must add the fields from each of these 3 sheets. So here the one with 2 sigma is going to produce a field twice as big. And again, that extends in all directions. And the one at 3 sigma is going to produce an electric field 3 times as big. And again, that extends in all directions. So what is the field, say, in this region here? What's the field in there? Well, from here we have a field of sigma over epsilon naught going to the right. From the 2 sigma one, we have 2 sigma over epsilon naught going to the right, and from this one, the third one, the field will be to the left, so we'll make it negative, and that's going to be 3 sigma over epsilon naught. So the field in this region here is going to be 1 plus 2 is 3 minus 3 is 0. So this might be the answer, because we've got a field E equals 0 in this region. What we also need it to be, E equals to 4 sigma over epsilon naught in another region. Well, let's look at this region here. Okay, this region here, if we look at it down here, well, we've got sigma over epsilon naught to the right from this charge sheet, and then we've got minus 2 sigma over epsilon naught from that one, because that's going in the opposite direction, and minus 3 sigma over epsilon naught from this one. Okay, and that's going to be sigma minus, so it's 1 minus 5 is minus 4 sigma over epsilon naught. The minus just meaning it's to the left, but it says we want one has magnitude is 0 and 4 sigma over epsilon naught. So this one works. So hence we have actually found our answer. You could just naturally go through these other 2 choices, because it could be more than one of these, so we need to check that it's not more than one of these. So what about this one? It's sigma, 3 sigma and 2 sigma. Okay, so in this region here it'll be 1 minus 3 minus 2, so that will be 4 sigma over epsilon naught. Beautiful. What about in this region here? Well, this will be 1 plus 3 is 4 minus 2, so that'll be 2 sigma over epsilon naught. And what about the outside regions, which I haven't worried about till now? Well, that's just the sum of all of them, so it's 1 plus 3 plus 2, so out here it's 6 sigma over epsilon naught. So you can see the second one here is not a solution because there's no region where the charge is, where the electric field is 0. The third one, again I can do it. If I go 2, I'm going to leave the sigma out now. 2, 1 and 3. Okay, so we can see again there will be a 0 region. Inside here it'll be 0 because you've got 2 and 1 pointing to the right and 3 pointing to the left. So that'll give us a 0 region. This region here, we've got 2 to the right and 4 to the left, so that'll also give us a region of 2 sigma over epsilon naught, and these regions as before will be 6 and 6. So this one also does not work. This does not produce the result we were asked for. So only A can be the answer. Okay. The key thing is, because they're infinite plates, the electric field near them extends forever. And the second key thing is that in any point in space, the electric field at that point is the sum of all of the different electric fields produced by the different sheets or charges. Okay. This is a nice one, quite easy. And it says we've got identical isolated conducting spheres 1 and 2 fixed in place, have equal charges plus Q, and are separated by a distance that's large compared with their diameters. There it is in figure A here. Okay. The magnitude of the electrostatic force acting on sphere 2 due to sphere 1 is F. Okay, so sphere 1 repels sphere 2 with the force F. Okay, now suppose that a third identical sphere 3 having an insulating handle and initially having charge minus Q is touched first to sphere 1, and when you touch it to sphere 1, what happens? Well, this had charge plus Q, right? Just checking that again. Yeah, plus Q. And we've touched that to a one with minus Q. So I think that the charge will distribute evenly, resulting in both of them being totally uncharged. Okay? So you now have a totally uncharged sphere. Q equals 0. And this one, of course, still has a charge of plus Q. Okay. Now, touch first to sphere 1, then to sphere 2. So when we go over here and touch it to sphere 2, we've got 0 charge there now. And now we have this with 0 charge, and this with charge plus Q. Well, afterwards, I think they'll both have charge of a half Q. So when we take away 3, finally removed in figure D, so now we have charge 0 here and charge a half Q here. And so what's the force? Well, originally the force was Q plus Q times whatever. Now it's 0 times a half Q. So 0 is the answer. Okay? I realised that, of course, as soon as I got Q equals 0 for that, I realised it doesn't matter what the charge is on the other one. The net force will be 0. Okay. The last question, and this is actually, it turns out, a really hard question, but it's not going to be hard, so let's do it. So we have a cube. There's our cube, and point charge Q is placed in the center, very near the center of the bottom face. Okay, and the flux through the top face of the cube, through this, is very nearly, is closest to what? Okay, well, we know that the total flux coming out of the out of the charge Q is Q over epsilon naught. And we know that half of it goes up and half of it goes down. So we know that, roughly speaking, half of the flux goes through the bottom face, so that can't go through the top face. Okay? But we also know that a large amount of the flux, we can see by drawing it, actually goes out of the side faces. It doesn't go through the top face. But some flux does. Okay? So we've got, like in these units, we have a total flux of 1, and we know that a half of it is going down the bottom face and a half of it is going up, and of the half that goes up, some of it is going through the top surface and some out through the sides. And so this answer that says the flux through the top face is 1, that can't be right, because we already know it can at max be a half. Then this one that says it's a half, that can't be right, because a half is what goes up, but a large chunk of what goes up is actually going out through the side faces and not through the top. So that can't be right. So we're left with this answer being the right answer. E depends on the size of the cube. Well, that's wrong, because it doesn't, because I drew a picture here. And did it matter what size I drew it? No. D, 0, you can say, well, it's not 0, because you can see that definitely some flux from that charge does go up through there, right? But that's not as stupid as an answer as you might think, because when the exact calculation is done, it turns out that the amount is actually 0.058, if my memory serves me correctly. And so it is closer to 0.1 than 0, so 0.1 is the right answer. Okay, that I didn't, when this was set by Paul Abbott, who no longer teaches here, and when he said it, I don't think he realised exactly how close this was and how hard it was. Well, he probably did, because he would have done the calculation. But it's the obvious choice nonetheless, C. Okay.